Welcome to Physics Can Be Fun with me, Stephen Thomas. Today we're talking about combustion. We're going to burn stuff, in other words. So we have three formulae on the board for you. The first formula is the combustion of carbohydrates. Now, commonly, wood is a type of carbohydrate. So when we light this match, we're burning a carbohydrate. Watch it burn. We add a bit of paper to it. There we've got two sets of carbohydrates burning. Let's put them in there. So that is our carbohydrate burning. We're burning cellulose, which is made out of glucose sugars. 6 carbons in each glucose, 12 hydrogens, 6 oxygens, combines with 6 oxygen molecules, 2 oxygen atoms in each molecule, forming 6 carbon dioxides and 6 water molecules. So when we burn something, we change from glucose and oxygen to carbon dioxide and water. So that was the combustion of a carbohydrate. Now let's have a look at the combustion of a hydrocarbon. Let's show you an example of combustion of a hydrocarbon. Here we've got a little gas tank, little gas burner. We can light it. And if you can see the flame there, we could, for example, roast a marshmallow over the flames. Can you see our marshmallows burning there? And there we have, in fact, a marshmallow is an example of this type of reaction burning. So this gas is a mixture of propane and butane, and here is the general formula for burning a hydrocarbon. Now propane, methane, ethane, propane has got 3 carbons. So let's stick with propane. What would the formula be? So we take 2CN. Now in the case of propane, it would be C3H 2 times 3 plus 2, 2 3 is 6, 7, 8, H8, so that would be 2 of those, plus propane, still 3 carbons, 3 3s are 9 plus 1, 10 oxygens, goes to form 2 times 3, which is 6 CO2, plus 2N plus 1, so that is 3 plus 1 is 4, times 2 is 8 water molecules. So let us in fact change that to 6 carbon dioxides, plus 8 water molecules. So there would be our formula for the burning of propane gas. Now if this propane were burning in a room that was oxygen deprived, so you didn't have any windows open, and after a long time all the oxygen got burnt up, the formula changes slightly. So what happens is, instead of producing CO2, we go and we produce CO, carbon monoxide. Now that's an odorless gas, and it clings to the hemoglobin in the blood, and it can actually damage the brain or suffocate and kill a person if they are in a room with not enough oxygen. So here is the formula. Have a look. It looks similar. We're going to, it's 2CnH2n plus 2. So it's still 2 C3H8. Now look at this. Instead of 3 and 1 is 4 oxygens, it takes, 3 3s are 9, 10 oxygens. It takes 2 times 3 is 6 plus 1 is 7 oxygens. So that's 2 3s are 6 and 1 is 7 oxygens instead of our 10, goes to form 2 times 3 is 6 carbon monoxides plus the same number 8 water molecules. So if in the exam they give you the combustion of a hydrocarbon, that is a carbon-hydrogen compound, in lots of air, well-aerated room, that would be your general formula. And if it's in a room lacking oxygen, that would be your formula. And so you see how instead of having 10 oxygens, we have 7 oxygens involved. Now, because we're talking about the combustion, for example, what would happen if we were going to burn a piece of coal? Or let us take what would happen if we were going to burn paraffin wax. Now, paraffin wax has got the formula, which is C25H, which is 2 times 25, which is 50 plus 2, H52. So C25H52 would be paraffin wax. It's in that area. Let's light this. So there is our lit candle. Now I want you to notice what has to happen before this can burn. Before you can actually get a candle to burn, you have to first melt the wax. The wax then goes up the wick, gets heated, forms a gas, and then combusts. And you will see that there's a little ring, and just above the candle you're going to get the orange and the yellow, and right at the bottom you may see a little bit of blue. So the combustion occurs above the flame. So in other words, what we're saying is, if you want to burn something, you have to first turn it into a gas. So if you've got a lump of coal or a piece of wood, you've got to heat it sufficiently that it vibrates, and it vibrates so much that it starts to fall apart. And at that stage, you'll start to see smoke rising from your piece of wood, that's the carbon, or your coal, that's the carbon, and then those little smoke particles, which is C, carbon, will then combine with the oxygen. So you've got to shake it apart so that the oxygen molecules can latch onto the carbon and combust it. So it's got to be in a gaseous form for it to burn. And that is why a fire has to be hot, and ideally a fire has to have a lot of oxygen. So getting off the subject now of hydrocarbons, I'd like to show you something which I think is quite interesting, and that is a thing called a rocket stove. Now, what is a rocket stove? Well, basically it is a big can. It's got one hole, and then it's got a can, then concrete or cement, then another can, and then more concrete, and then another can. Now the idea of this rocket stove is to create an area in the combustion chamber which keeps in the heat. So the concrete or cement, being a poor conductor, keeps in the heat so that complete combustion occurs. And when there's complete combustion, you don't get as much smoke coming out. And then you take your little sticks, and there's a little platform where you can place your sticks in here, and normally you use small little sticks like this, and your sticks sit there and the oxygen comes in from below. So this little platform is just simply a piece of metal with little edges here to stop it going all the way in, and so this creates a very hot flame because the heat is contained in here, and because it's so hot you get very little smoke coming out the top, and this little platform allows it to burn, and then oxygen can come in from below. Or you can drop the sticks in from the top, and you could light it from here or put a piece of paper in and light it. Now, a Mark II version, an even better version of a rocket stove, would be something like this. Now, what have we got here? Can you see there's a little computer fan? And if we attach the computer fan to a battery box, there we go, there's the black wire, there's the orange wire. Can you see that when we place the battery in, do you see how our fan begins to spin? Now, what are we going to do with this fan? We're going to put it here by this opening, like this, and now oxygen is going to be blown into the entrance to our rocket stove, and you will feel air coming out of the top. Let's just see if we can point that like. Okay, that pulled out. So let's do that. So there you can see our little stove spinning, our little fan spinning. I'm going to take a little piece of newspaper, I'm going to show you with a few twigs our rocket stove, light it, put it in at the top, put in a few twigs, I think our paper went out, so let's get another little piece of paper. And there's our rocket stove, burning. Little fan sucking in air. I'm going to switch off the light so you can see it better. And look how well our stove burns. So it's the combination of, now listen to it. Can you hear that sound? So it is the air coming in, and look at how it burns. And listen to that sound. And it's going to just burn itself out now. So I think that this is a fantastic little stove. We are using a renewable resource, which is basically wood. Did you see how few little sticks I needed to get it going? And it started to roar. Don't know if you can hear that, but when it roars. And look how little smoke is actually coming off from our rocket stove. And now we put a little grid on top, and we can boil water, or we can barbecue a steak on top there, and it's due to our motor forcing air in at the bottom here, and there is our rocket stove.